introduction. And also very excited to be part of this new Data Sciences Institute of the University of Toronto, and very happy to co-lead the reproducibility theme with Jason and Jay and Rohan. So today I would like to discuss a little bit our experience in the not so hard path to transparency and reproducibility in machine learning and AI research. So I'll share the all the slides after the talk, but feel free to ask any questions at the end. Okay, so those are my disclosure. The only one that's really relevant to this presentation is that I'm a consultant for CodeOcean, which is a platform for reproducibility. Okay, so this is probably the most important picture of the whole talk, which is a very nice picture from cartoon from Sidney Harris, where you can see this very complex theorem demonstration, let's say. But then in step 2, there is kind of a miracle. There is something that is not fully explainable. And as a scientist, it's very hard to build upon a miracle. And there are many, many miracles in published literature, unfortunately, many steps that are either unexplained or very poorly described and documented. So in our field of computational reproducibility, especially for AI and machine learning, it should really be easy. You just have to run the same computer code on the same data to obtain the same results. So that's kind of a very, very low bar, if you wish, in terms of reproducibility. But you'll see that even that is not that easy peasy, actually. There are many components that are required to ensure full computational reproducibility. And so in theory, it's completely achievable. We're dealing with deterministic machines. So if you share some key components, it should be fairly easy for somebody independent to follow kind of the recipe and run the code on the same data, get the same results. However, as many of us know by now, just reading a paper, downloading the code, accessing the data is not often enough to reproduce the results. Not even exactly the same results, but even getting close is very often super hard. And so why does that matter? It matters mainly because nowadays in modern computational sciences, data analysis pipelines are becoming increasingly complex with a very, and therefore a very high level of transparency is required to be able to scrutinize and reproduce a study. And those analyses become very complex also in terms of the number of parameters that could be tuned to generate the final result. So assessing the robustness of the claims in a given scientific publication is becoming very challenging as well. And what I think is probably one of the most important and most exciting part of reproducibility is that if you manage to share all the components of your study, people can actually reuse that materials, those research outputs, to do something completely new and unexpected. And therefore, you have a higher impact and return on investment on the data you generated and the algorithm that you created. So here I'll present the key elements of a very typical machine learning and AI pipelines. So bear with me, it's overly simplistic, but just for the sake of the presentation, it will allow us to go through the main components of that are required for full reproducibility. So first of all, you start with some raw training data set or discovery data sets that you want to analyze. So you want to do your quality control and pre-processing. This is important in all the fields, including mine, pharmacogenomics and radiomics. And then you get those process data, those data that are amenable for analysis, and hopefully that are more standardized and more complete after all this pre-processing and annotation process. Then you train, let's say you want to train a predictive model, you train your model on those training data, and then you get this final model that you would like to test in the real world. And obviously, there is a lot of issue about overfitting and such. So you really want to keep some data aside, whether you call it raw validation or testing data, that you never used for training the model. And you want to go through the same process of QC and pre-processing completely independently. You get your process validation or testing data. And that's where you really test the performance of the model on this new unseen data. So in this very simple schematic, you can already see that there are two two steps where data are heavily being worked on. So the acquisition of the raw data, as well as the processing and quality control of the data. And then there is code for quality control and processing, but also for model training. And there is code representing what the final model is. And then this final model could be packaged into an object that could be used for independent validation. And so you would think that sharing the code and the data as well as the model is enough to reproduce a study, but actually something that's often overlooked is that the initial investigators or authors actually run that code and data and develop that model into a specific software environment. And that needs to be specified very, very clearly to be able to reproduce exactly the analysis pipeline and the final results. So I'll go through all the different steps and really kind of showcase that we have tons and tons of technological platforms allowing us to easily share all those components. So it's not really research reproducibility. It's not so much of a technical issue. 90% of the time you can easily use existing platform to make your study reproducible. Of course, there are some edge cases where use is very specific hardware, very large scale computer clusters, and it could be a little bit harder, but most of the time, the vast majority of the studies could be made reproducible using existing technologies. So if you want to share data, and they can be publicly shared because they're not sensitive, you can use very large, you can use established repositories such as the European Genotype Phenotype Archive in the genomics field to share those very large files. There could be dozens or hundreds of terabytes, but there are many established repositories to do this. If those are small files, usually processed data using the machine learning and AI, there are multiple resources such as Zenodo or Harvard Dataverse, Dryad, or Figshare, where you can easily share those files. Now, if those data are private or sensitive, and that's the case, for instance, for patient health information, then you can still share those data, but you just need a layer of protection. And one way to do this is to have a data access committee or DAC and a transparent process to review the request. So as a researcher, I see a publication with a very exciting but sensitive data set. I would send a request to access that data, say, hey, I'm a researcher, part of an eligible institution, and I would like to do this on the data. And this access committee will review the request and basically accept it if you do nothing really crazy. And you basically have to sign a data usage agreement most of the time. The tricky part here is that institution must put a timeline associated to that process review. Otherwise, it could take months or it could take 2 years. And if there is no accountability on the timeline for that process, it becomes very hard for independent researchers to kind of rely on those data for their own research. There are many established repositories that can forward the request to such a data access committee. So you don't really, as an institution, you don't really have to deal with all those requests. You can easily use established repositories for that. And EGA or dbGaP in my field is doing that very nicely. And you also want to use a platform where data transfer is actually secured and automated. I had cases where after 2 years of ordeals, like back and forth with the lawyers, we finally get the agreement, and then then they send me all the data on hard disk. And I have to basically talk to my sysadmin, get those hard disks connected physically to the server, which is a big deal. And this is really not ideal. So there are platforms doing encrypted, secured, automated data transfer in a very effective way. So use those instead. When you sharing the computer code is actually the easiest way. Those data are extremely lightweight, and there are many platforms to do so. So as I said, there are different levels of code, but you can categorize them into processing, training, and validation in our case. You can use versioning systems such as GitHub or Bitbucket, for instance, very standard in any computational fields and software development. If you do AI and machine learning, there are kind of frameworks that you could use, such as PyTorch or TensorFlow, even higher level frameworks like Keras and PyTorch Lightning, that kind of forces you to organize your code and make it easier to read for the community. Obviously, documentation is a must. We never document our code enough. And also, you probably want to think about the license very early on. Do I want to make it open source, which I hope you do? But do you want to put any constraints in that open source license? For instance, do you want it to be used by the research community but not by companies? Do you want to put a non-commercial clause into your license? So think about that before you share your code, obviously. And so the models themselves are very useful for the community. So once you've done your pipeline and you have your final model, it's kind of fully frozen and ready to be applied on new data, there are platforms to allow you to easily share those models, their architecture and full set of parameters with the community. And Model Hub, Model Depot, and Model Zoo are three examples. If you really want to be nice with the community, couple your model with an example of code to showcase how it could be used on your data. So describe how to format and process the input data, how to interpret the outputs, and try to describe the limitations of your model. Maybe it has been designed in a way that it only works in certain scenarios, and that should be documented, not to prevent other people to use it in other scenarios, but at least to have a warning saying that it was not meant to be used that way, and so caution must be taken. And something that's relatively new is that we realize that models, especially complex models, may reveal key aspects of your data sets, especially if some, in the case of genomics, for instance, if some patients in your data set have very, very specific features, it might be reverse engineered that that patient is part of your data set. So it's still fairly low risk, but differential privacy can sometimes be ensured. It's definitely something worth paying attention to. But maybe most importantly, that doesn't mean you cannot share your model. It just means that you need some level of protection when people access your model. So if you can share the raw data, which obviously are the most sensitive aspect of your study, you can definitely share your model the same way behind a data access committee. So there is no reason why the model cannot be shared with the community. And so the final piece, which is all the software environment, I call it the power of virtualization. Now that we can really virtualize and build containers or virtual machines to run any piece of code in a reproducible manner, it's really now the time to use these kind of technologies in science. And so defining your software environments, basically it's all about defining the operating system, the software libraries, and the exact versions of those libraries. Sometimes you can even go even further and restrict the type of hardware that may be used. So go virtual, build virtual machines and containers. So you can specify all those aspects, all the libraries and their versions. And once you build a container, you can easily add your code and data, complete a successful run, check your results, and voila, you can easily share it with the community. And so the beauty with such a virtual machine is that it's very, very easy for the people to reproduce your results, but also scrutinize and challenge them. They can easily change one parameter. They know it runs by construction, so they can change a parameter and see how it affects the results. And there are many platforms that exist to build and share those containers in the cloud, such as Gigantom, Docker Hub, or CodeOcean. So I'll go through a few kind of case scenarios where we'll see the different levels of reproducibility. So for instance, obviously this is the perfect study where everything is being shared: the raw data, the code for quality control and pre-processing, the process data that are analysis ready, the code for model training, the final model itself, and some code to use it, as well as the full software environment. So once you get all those elements, it should not take really long, too long to be able to reproduce the results. It's all about the compute time. There is no time wasted in trying to make the code run and trying to understand the code and modify it. So everything run by construction. So it's really helping the community to build upon your study. But this is obviously not very common. There are very few publications that go that far. Even so, that should be the goal for any of us. So very often, people don't share the raw data or the code to process those data, either because they don't feel like it's relevant or because it's from a legal perspective, it's really hard to share the raw data. there are always good reasons, or actually there are always bad reasons not to share those things. But the reality is often the raw data are not available. But if you have access to the analysis, the process data, and all the rest of the code as well as the software environment, then at least people can they're probably able to reuse your data, reproduce some of your reproduce your results, trusting the process data, and reuse the process data for other studies. So it's still a very valuable study for the community. But if you can document how the raw data and the processing are being generated and done, that's definitely better. However, if there is a new processing approach for the raw data, or if people want to do a meta-analysis at a very low level, they won't be able to do so because the data and the pre-processing code is not available. Now, unfortunately, this is very common in computational research, or at least in biomedicine, is where none of the data is being shared, not even the code for the study. But if you're lucky, at least they share the final model, whether it's a list of genes or formula or deep neural net. So at the very least, you cannot reproduce this study, but you could use this model for something else. You can validate it in your own data set. You can try to modify it. You can use it for transfer learning. So there is still something you can do with this study. And I call it the level what the heck is actually very common, that people don't share a single thing. And that is especially true. A trend I see in the literature is that industry is coming in, they have those beautiful papers where they describe all their great models and stuff, but they don't share code, they don't share data, because they don't know them, they don't own the data, or they don't want to share them. And the code is trade secret, or it's like too complicated to be shared, right? And so at the end of the day, you're left with a beautiful piece of text that I would argue is pure advertisement. There is nothing you can really do with such a study. There is no research outputs you can build upon. And I would like to paraphrase John Claerbout here, saying that in computational research, the actual scholarship is the full software environment, code and data that produce the results, not really the results themselves. And so something that is also become more and more evident is that as we get more and more resources, especially those big companies who have access to extremely large pool of GPUs, for instance, or very specific hardware, it becomes very hard to reproduce a study, and the models are becoming increasingly complex. However, not sharing just because you have access to something unique is kind of stupid in a way, because it's just a matter of time until the technology catches up, and you can basically rerun that model, maybe not at the time of publication, but a few years later. But also, there is a lot of research that can be done in trying to simplify the initial model. Either you have a more sophisticated way to train the model, more efficient way, or you just want to simplify the method and the model and see whether you can reach the same performance. So there's a lot of very cool research in trying to derive models from simplified the initial models. And so in my lab, we try to focus on reproducibility at multiple levels. So the best case scenario, which requires a lot of time and resources, is to really care about reproducibility over the course of the full analysis. So from the get-go, you only work in virtual machines and containers, and you really make sure that everything is reproducible at any time. And it's a great tool for collaborations because people are basically working with always the same software environment and piece of code. Sometimes we do it a bit later, where we do it just prior to the manuscript submission. You want to make sure that your results are reproducible. So what we do in the lab is that we have somebody independent reviewing the code, and we run all the analysis from the raw or the low-level process data if it required a lot of resources to process the data. And then at the time of the manuscript submission and during revision, you will be so happy to make your result reproducible when the reviewer is going to ask crazy stuff and you're going to have to redo a lot of analysis. I can tell you that's really where, when you feel that this investment in reproducibility was worth it. But it also happens after publication. So sometimes we had collaborative papers where we could not force the authors to kind of wait to make everything reproducible, so we kind of work in a parallel track. Or sometimes people question your study and you really have to go back and try to see if you can improve the way it's done, or you want to change the parameters, prove them wrong, or show that they're right. So after the post-publication aspect is also very important. So the lessons we've learned in the lab is that it really takes time and expertise to make your research fully reproducible. So there is no reason why this kind of activity should not be part of the budget of your grant proposal. I think it's a very important aspect that's often overlooked. Make it at the center of your lab's modus operandi. Even discuss it during interviews when you want to hire people. Say, what do you think about research reproducibility? What are the techniques or the platforms that you use? Just to make sure that they understand that for you it is very important as the PI of the lab, but also that it's kind of a mindset for the whole lab. And honestly, make it mandatory. This is not a bonus nowadays. I really feel like this is part of the scientific process, and making your research transparent and reproducible should be part of the culture of the lab. But you're going to have to resist the pressure. We computationalists, we're always in a hurry to publish. But editors and reviewers appreciate transparency. I would say 5 years ago, I never had any comment about all the efforts we put in reproducibility. But nowadays, I would say in 50% of my submissions, we got reviewers really applauding us for all this code and all those data and all the software environment that we share. So it's really trying to pay off. And it's an investment. When reviewers' comments going to come back, or when people criticize your study, you'll be very happy to be able to reproduce the results and modify the code and generate new results easily. So something that's really kind of human-centric is, if you know that you're going to have to share your code, honestly, you make a much better work, a much better job at making it high quality. You know that this scrutiny that you're going to kind of put yourself, that you're going to allow the community to do, is really going to push you to do the best. It also makes it easier to collaborate, as I said. Like if you deal with the same software environment, it's really much easier to run the code and on the same data. It really increases impact. In my short career, I really figured out that when you share, those are really opportunities for new collaborations. People just won't steal your data or steal your code. They're going to use it with or without you, and with you more often than not. So I really enjoyed this kind of collaborations where people contact me and say, hey, I'm very interested in that, but I'm not fully familiar with this. Can you help us? And this is really cool. I think Jan Joly will probably discuss this, but open science and research reproducibility do not prevent commercialization. Even if you have open source license on your code, you can still generate revenue. It's not straightforward, but there are many companies that have a hardcore kind of open source product, but still can generate a lot of revenue on their enterprise version, let's say. And making research reproducible doesn't make it right. You can still get it wrong, but at least you can go back and fix it. If you don't share anything, the community will probably take years to figure out that something is really, really wrong. So, this is really slowing down research if you don't share. And so at the end of the day, research reproducibility really equals to impact. If you make it right, if you document everything and you share the right research outputs, then you're going to allow the community to reproduce. And that's going to mean it's better for the field, it's better for you, it's really better for the whole community. So if you're interested, we've published a commentary about this regarding all those platforms that I discussed today. And I would like to highlight that Michael Hoffman and Joel Pinot are going to give keynotes on Friday. So that's also very, very exciting. So with that, thank you for your attention, and big thanks to the many people who participated into those discussions. Thank you very much.
Thanks very much, Ben. There's a question from Saren. Saren, would you like to ask a question?
Yeah, thanks, Ben, for your presentation and your suggestions. My question and only quandary is from like from a cultural perspective, what in practical, like I know you gave some really good examples and advice just regarding what are things that researchers can do. However, being able to actually put these into practice requires, I think, more than just your individual labs or your peers or your circle of fellow researchers and colleagues, to just be able to actually systematically change how you share code, share models. And my question is particularly focused on those inferential models or methods that you can only do these in very, very high performance computing environments. And particularly, I'm struggling to understand how those can be, extended or critiqued when at the end of the day, you don't necessarily have the funding or the financial resources just because of how there's disparities in just how funding is allocated, at least in Western academia. And how do you actually come up with a way to encourage those researchers and at like say Google Brain to be able to checkpoint and post each of their models or each of their revisions to like some sort of Docker container that can be just easily pulled and then reproduced. I'm just trying to understand, how do you, at the end of the day, what do you try to concretely tell people to do, or like actions that you can actually motivate people to actually change their behavior when, I guess.
I think there are probably three aspects to your question. One is sometimes institutions make it hard for you to share, right? So they may want to protect the IP. They may think that this data is too sensitive to be shared. And that's very hard from a researcher perspective, because you're not going to change your institution's policy like in 24 hours, right? So you really have to kind of push back collectively and say, no, this is my duty as a scientist to share those data, because one, it's important for the publication. I just want to push out. Second, it's important for the field. We're going to move forward together much faster if we start sharing more data and models. So that takes time, but I can tell you that if the institutions are being assessed by the number of publications, the number of grants, and this kind of stuff. If you basically tell them, I cannot publish in, I don't know, science, let's say, because I cannot share my model, you'll figure it out that they can unlock some of the doors for you, right? So you also have to understand their own incentives and kind of play the game and push back a little bit. I can tell you from, I'm getting slightly allergic to IP. So I told my institute, everything I do is open source. So deal with it, right? And so far, so good. They always let me, publish all the code I wanted. Maybe the tech transfer department is not always thrilled, but I don't care. I think this is what I do best as a scientist. I contribute more if I put my code as open source. Now, the problem of not having access to very large scale infrastructure to be able to retrain from scratch, that's definitely going to be a problem, right? But unless you use quantum computers, there will always be a way. It's just a question of money, right? So when companies tell you, oh, I'm using this super kind of specific internal kind of resources and I cannot share the code, honestly, I think that's BS. Any code that you share would be valuable. Maybe you cannot run it, but there is a lot to learn from any piece of code. Unless you encrypt it, there is always something you can learn from piece of code. So you can always share your code, even if the researchers around you don't have access to the exact infrastructure. Obviously, to reproduce that kind of study, it's going to be a big deal. Like you're going to have to modify so many things to get even close, right? But it's better than not sharing anything. When it comes to having access to large-scale resources, luckily, institute like the DSI, the Data Sciences Institute, have mechanisms where you can basically, for instance, I got a grant to access a data set. It cost me $6,000 to access it on Google, and maybe as much to store it locally before processing, right? So this cost of just getting the data is definitely prohibitive. Luckily now we have mechanisms where you can apply and say, hey, I really need large amount of funds to even get the data, run that code. And hopefully you can, do your research that way. It's always going to be limited and competitive. But keep in mind that if it's not possible today, maybe in 5 years, it's going to be fairly trivial, right? So I think the computational requirements is also moving targets. And you don't really, it's too bad if you cannot reproduce a study the day of its publication, but if you can reproduce it 5 years after publication, it's still quite valuable. There's still a lot of stuff you can learn from it.
Okay.
And I forgot the third part, but I hope I answer. Most of
Yeah, I mean, you gave me some good ideas in terms of how to frame certain things. So this is helpful. Thank you.
So we'll go to Stephen and then probably our next speaker, Colin. Stephen, question?
Hi, thank you. I really enjoyed your talk. Thank you, Benjamin. Can you give any examples of when you have shared code and data during the peer review process of any sort of, or subsequent to the peer review process, of any sort of new spontaneous collaborations that have emerged that you wouldn't have predicted? You sort of hinted at it during your talk that, you know, things will come of it. I'm just wondering if you could give some examples from your lab.
So during submission, it's a bit more rare, but I got one reviewer actually suggesting a modification of the code that really worked well, right? And that's really cool. So not only they looked at the code, they appreciated the fact that we shared, but they actually were so interested, they actually dive into the method and made very useful suggestions. So it might be very hard if you cannot run it easily, but now if you use stuff like CodeOcean, where you literally one click away to run the code in this Docker container, I mean, it's super easy for the reviewer to look into the code, change one thing, run, and see whether it works, right? So I think that was one very, very cool example. Most of the examples I have, it's like people read my publications. They can access the data, they can access the code, and they can do the analysis I've done in my paper, but they want to go further, right? And either they do it on their own because they're expert in the field, or very often in my words, like those are biologists or clinicians, that they come to me and say, hey, you're the machine learning expert. We're very interested in this, but we want to modify this a little bit, or we want to apply it in our own data. Can you help us? And usually those are very exciting collaborations because we start with the same kind of understanding. Like we agree to use this kind of framework to do something together. So the collaboration is very much streamlined. You don't start with a big question and then you try to figure out how the analysis pipelines and stuff. No, they already come to you because they like your pipeline, right? So it's kind of easy for me then to contribute to their own research. So I think that's really the power. And even if they don't come to me and just reuse my work, I mean, first of all, that's a success from a scientific perspective. And second of all, you kind of get a good reputation in the field that will help you indirectly in many different contexts. So I really felt that sharing has a lot of indirect effects that I didn't expect early on. I thought it was like a lot of investment for not much return, but now I realized a few years later that this investment actually has a huge return on investment directly and indirectly.
And just final question from Moni, and then we'll move on to Colin. Moni.
Yes, thank you, Rohan. Actually, this is a kind of question and kind of opinion. What I'm trying to say is that sometimes I felt it. I cannot say it for sure, but sometimes I felt people don't want to share their whole process because some research labs, they have continuation of research, and you know there is a pressure of publication, like you have to publish on top of that. So when you find a good machine learning model, or like I work in a reinforcement learning, so we try not to share much the hyperparameters or reproducibility things, so that if I easily people get the model, the next paper what we are planning to publish, they will publish before us. See, so this is one point I think which also works among the researchers. It's a bit psychological, bit academic, you know, hassle. Yeah, that's the point I wanted to make.
I mean, we need a couple of beers to go through that. But thanks a lot for asking that question, because that's how a lot of people are thinking. You have to define what impact means to you. If impact means that you can publish your next paper, great, keep everything secret, don't tell anybody, right? If impact is that you contribute to the field by inventing a new method, sharing a new data set or whatever, that's probably where your reputation is going to be much higher, your impact overall is going to be much higher. And you know, honestly, who cares about your next publication about these specific models? Unless you want to build a company around it, what really you should look for is having a positive impact on a whole field. I really feel, I can tell you my personal opinion, people that are being protective about their research outputs, have an order of magnitude less impact than people sharing. That's, for me, it would be hard to quantify, but it's obvious in so many ways, right? So you don't lose by sharing. You gain much more than what you share. So I don't really think that protecting your pet models or hyperparameters or data set is really the right way to get the highest impact. It's a very short-term vision, and it might be beneficial short-term, but it won't be beneficial mid and long-term. Personal opinion. Don't be offended. Just be.
Right. Thanks very much, Ben. Really appreciate your talk, and also, yeah, just being able to work with you a little bit as the co-leads has been really wonderful for me as well. So thank you very much.